Hello and welcome to TD Physics. We're going to be looking at vector addition and components today. As part of our memories and history, we left off with sapper Stan Gilmore, who was a Canadian engineer who was a sapper, and they were responsible for digging the long, dark tunnels underneath enemy lines, packing them full of high explosives, and ideally getting out of there before they erupted. They were some of the largest explosions by humans prior to nuclear weapons. And with war, there was a lot of leftovers, unfortunately, and collecting was not uncommon. There were some American soldiers with German helmets, and here is another American soldier with a belt. These belts had a curious name. They were called hate belts or souvenir belts. And this is the one that I purchased last year. They think the name hate belts originates with individuals collecting cap badges and other souvenirs of those enemies that they had overcome. But they also were more commonly souvenir belts where they collected them from allies. This particular one that I've collected has all British and British ally badges on it. Towards the center, you get to see the rising sun of Australia as an interesting badge. And there's only so many places where all these different battalions overlapped. And so to the best of my figuring, this came from Egypt during World War I. So that's your moment of history. Know your history, know your physics, and let's get into some component method vector addition. So we've looked at vector addition and looked at a couple of applications for it militarily. We're also going to be looking at a more mathematical approach to it. The scale diagrams are good for communicating, just big picture visuals. They're real handy if you do not have a calculator or a computer to do some of this work for you. But ultimately, being able to be super accurate is very important, especially as technology does a lot of work for us. And so we practiced some trigonometry in grade 10 math, I believe, and as a review in grade 11. And so if we're going to take a vector, okay, and so it's something in this ballpark right here. So we're going north 30 degrees east. Okay, and so if we were careful and measured this out with a protractor, we'd find that that is 30 degrees. And we're reminded that north is up and east is to the right. Or any vector can be expressed in terms of a x component and a y component. In physics, I like to draw my components as dotted lines to indicate that they are kind of more of a mathematical idea. And so we've got here, we've got a horizontal component and we have a vertical component. And mathematically to find those, we need to use sine and cos. In pure math, as you get further along, mathematicians are a big fan of measuring all their angles from east. And if you do so, there's something that's kind of tidy that works out in this method, because if you measure all of your angles from east, so for example, this would be 60 degrees, and say you were measuring down to south, so that would be 270 degrees. If you measure all of your angles from east, going counterclockwise, there's a bit of a cheat that we can use here to organize all of your x and your y's, and it will even do your negative and positive values for you. Now, I'm not a super big fan of that. I prefer to draw out each individual triangle, visualize it, and remember that north and east are positive, south and west are negative, but it's up to you. No matter what, though, you need to be able to recognize that sine and cos are used in different circumstances for different things. So I'm just going to take that little bit of explanation away and leave us with where we started here. So if we're going to go and figure out what these, or where we got these numbers from, if we are going to look at this component right here, well, if I'm looking at 30 degrees as being my angle between my vector and my axis that I'm measuring from, well, if that's my angle in here, then I'm going to be using opposite, and I'm using adjacent. Opposite and adjacent. Remember that you've got SOHCAHTOA. So if I've got opposite and I've got a hypotenuse, then I'm going to be using sine. So sine of 30 degrees is equal to my opposite, which in this case I don't know, but it's my x component, and it's over my hypotenuse, which in this case I know is 10. So I bring this up here. My opposite is equal to sine 30 times 10. So my opposite, or my x component, is going to be sine of 30, which is 0.5 times 10, which is equal to 5. So that's where we got our first answer here from. 5 meters east, and that's where we got the number 5 from. We also need to look at our second situation right here. How do we find out how far north this is? Okay, well, it's a similar sort of process. We'll use a different color pen to emphasize that. If we're going to find this edge right here, so if we're going to figure out how far north it is, then we're going to need cos, because we have our adjacent angle and we have our hypotenuse. And so for this one, cos of our angle, which in this case is 30 degrees, is equal to our adjacent all over, again, 10. And cos of 30, I've done this enough times to remember that's about 8.66 times 10. And so we just simply move the decimal place over 1. And so that's how we're going to get this, our 8.66 meters north. That's all a component is, figuring out how far north did you go, or south, and how far east or west did you go, even though if you didn't do them separately. Okay, so we're going to skip over this one unless you really want to explore that more on your own. Okay, so I prefer that, at least in my world, I look at every single vector individually. So what happens if we look at a few more examples? So I'm going to page down here one level. So what happens if I break up these three vectors into their components? Well, I'm going to zoom in a little bit closer. There we be. So if we're going to take vector A, so here we are, and there's a vector A. 59 degrees is measured from north going east. And so if we're looking at vector A, then what we're looking at here, if we're going to look at our x components first, or I guess we'd look at this as our left-right component, what we're going to find is that, well, we're trying to find this piece. And so I'm going to draw this in with a dotted line. There we go. And so if we're going to find what that is, what we're going to have to do is, that's our opposite from 59 degrees. And so opposite is sine, if it was that over its hypotenuse. So sine of 59 degrees. And what we're going to do is we're going to just simply write this out as one step. So that's going to be times the hypotenuse is equal to our opposite right here. And so that is going to be equal to 0.857 times 59. So that's going to give us approximately 50.6 kilometers, and that's going east. And we're going to identify this one as a positive. Moving forward, north and east are positive. South is going to be negative, and west will be negative. Why is that going to matter? Because we're going to be doing addition soon. Okay, and then if we're going to do our next one, if we're going to do our y component, and so that's going to be how far up this one is. So again, if we're going to be looking at this as a little dotted line, that's what we're looking for right here. Well, in this case, if you're looking at it from this side right here, that's also going to be the same as this side on the left. So we can either use sine of the leftovers of 90, so that'd be sine of 31, or we can also use cos of 59 degrees, as these are the same length. So that's what I'm going to do. I'm going to use cos of 59 degrees times 59 is going to be equal to my adjacent. And if that's true, then I'm going to get, let's see, cos of 59 is 0.515 times 59. So my adjacent right here, 30.4 kilometers. And in this case, it is north. So that's also going to be a positive. Okay, we'll do this a couple more times just to get in the habit and make sure that we're comfortable breaking individual vectors into their components. And then we're going to get a little fancier, and we will add two at the same time. Okay, so if we're looking at vector b, well, if we're looking at, again, x, well, what do we have for angles? We've got 30 degrees in here. And so if we're going to look at, I'll change the color of our lines here this time. So if I'm going to find my horizontal, that's right here. Well, if I'm going to find that horizontal, or how far west it is in this case, this is going to be sine of 30 degrees times my hypotenuse, which in this case is 40. And that's going to be equal to my opposite. So that opposite is equal to sine of 30 is a half exactly. And so this is going to be 20 kilometers going west, or later on, once we start doing addition, that's going to be negative. Let's speed this up a little bit. Cos of 30 degrees times 40 is equal to our adjacent. So cos of 30 is 0.866 times 40. So the adjacent in this case, this is going to be north. I'm going to work my way backwards on this one so that I make sure I have space. And that'll be 34.6 kilometers north. Okay, and so that would be this one that we just found right here. And again, remembering that this and this, these two northerly vectors are the same distance. And then finally with C, last bit of practice before we add another one to it. So if this is C right here, so vector C, we're looking into its x component. Well, what's our angle? 17 degrees. It's measured from south, our horizontal right here. That is going to be sine of 17 degrees times 36 kilometers. And that's going to be equal to our opposite. So our opposite is equal to, let's see, sine of 17 is 0.292 times 36. And so that makes our opposite here to be 10.5 kilometers. And you'll notice that this is going west. It's going that way. And so that eventually is going to be given a negative value once we add things together. And again, if we're going to figure out what our vertical is right here, I don't care which side you're looking at that on. Here we go. Cos of 17 degrees times 36 is equal to our adjacent, or our up and down, or north-south. So the adjacent cos of 17, I believe, is equal to 0.956 times 36. And so our adjacent in this case is 34.4 kilometers south. And this would also give us a negative value as we get into adding these sequentially. And so that is round 1. So you saw in the Australian historical video, some of the techniques that were taught to infantry to map out all of their different displacements and how to add them together. And that's what we're going to be doing this time, just in a different method. So here's a bit of a step-by-step reminder of how to do that. So first of all, we're going to just make a light sketch to make sure we've got just a fuzzy picture of what's going on. It doesn't have to be perfect. It doesn't have to be perfectly scaled, or the angles don't even have to be 100%. It just gives us a rough idea. Then we're going to break our vectors into components like we've been practicing. And then once we've all got our x's and our y's into columns, then we're going to straight up add or subtract them depending on the sign. And then we're going to do Pythagoras to them. Okay, so that's, we'll go back to this list again in a moment. Okay, so let's get a specific problem. We won't do quite as many little ups and downs like the Australians hunting for large guns. We'll go for a more passive example right here. Okay, so we got a sailboat, and it's going to go north 60 degrees east for 20 kilometers. And we have to decide on some sort of reasonable scale here. But this is just a rough sketch. So as long as my 20 is bigger than my 12, I'll be fine. Okay, so I've got a little handy dandy estimator here for me to let me know that that's about the right number of degrees. And so that's this one right here that we're looking at. And the second one is the wind factor, which is going to blow things. Now, notice that this is west 25 degrees north. So that's a little bit trickier. I'm going to make this one to to be shorter and be somewhere in this ballpark right there. So what's the net result of those two vectors being added together? By the time this was all done, what we should find is that somewhere in this neighborhood is the final answer. And again, I like to try to draw. So we should find that somewhere in this neighborhood is our final answer. That will be our total displacement for our sailboat. Okay. So it should be something north, and it should be something east. And if that was 20 and that's 12, my best guess, if that's 60 degrees, then I'm going to say that this is about north 30 degrees. This is completely a guess, but I'm going to be using this to check my actual answer. Okay, and my final, the distance part of displacement, if that's a 20 over here and that's a 12 over here, then most likely that's going to be, say, I don't know, somewhere in the 16-ish range, 15, somewhere between 15 and 17 kilometers. Okay, so again, that's a guess. The more careful you are at drawing it, closer you are to scale, the better your check will be. Okay, so there's my first step. So there's my sketch. I got to convert my vectors into components. So that's going to be a bit more work. So on the next table, or the next page, we've given you a bit of a table right here. And so we've got vector A and B. So that's due to the wind, just to differentiate them. And so this is our magnitude. Okay, so these lines are an absolute value, so we're not assigning a plus or a minus to them right here. Okay, and so that was 20, and that was 12, and our units are in kilometers. Now our angle, we have to decide what we're going to be measuring from here. And so if I'm going to be measuring the number of degrees I have, okay, well, I'm going to do this from x, do something a little bit different. Okay, so remember that we have to be able to be responsible enough to look at a triangle, and if you've drawn it well and your angles are reasonable, you should be able to double check your work. So I'm going to say this is 30 degrees, and I'm going to emphasize that this is from x, and that would make our B 25 degrees from it. Okay, because again, that was west 25 degrees north. And so that is 30 degrees in here. Okay, so we're going to be finding a few different parts. We'll highlight them as we go. So for our x component, okay, of part y, well, we can use some individually color-coded things here. We've already used hot pink one other place. Okay, so the first one I'm going to do is this one right here. And so that is my A in the x component. 30 degrees is my angle. So my x component will be cos of 30 degrees times my magnitude, right? And that was 20. And so that's going to be 17.3 kilometers. And that's going to be east. I've gone ahead and filled in the rest of these squares just to speed the process up a little bit. But you can pause it if you need to slow things down. So sine of 30 times 20 is going to give us 10 kilometers north. Okay, so again, what will that look like up top? Okay, so that'll be giving you your northerly part right here, the A to the Y. So now we've got our A to the X and A to the Y, horizontal and vertical. Let's head back to this. We're going to look at B as well. And so for B, when we're looking for our X component, so that's going to be cos of 25, again, because we took our angle relative to horizontal, times 12, gives us 10.9. Now I've highlighted the negative here. So notice that that negative is because it's going west. Okay, so our first one was east, next one was west. So those two are going to fight against each other a little bit. Right, so this one is going east, this one is going west. But both vectors go north. And so our secondary component right here, the y component for b, sine of 25 degrees times 12 gives us 5.1. And it's going north, so it's positive as well. What this means is that if we're going to look at our totals now, of our x's, because they're going in opposite directions, one's going east, one's going west, they almost cancel out. We're down to about 6.4 kilometers, and the east wins by a bit. And the y component, we've got all of them are north, and so 10 plus 5.1 gives us 15.1 north. We're constantly going north in some manner. So our final step, or final steps, are going to be to combine all that horizontal and vertical information we found. So I've put it as a sketch onto my grid here, and I'm using Pythagorean theorem. So this will be the last time that you ever see me fill out Pythagorean theorem unless someone's in a real tight spot, because I'll just assume that you know how to do it. And so if my sides are 15.1 and 6.4, I discover that my hypotenuse, my total displacement from where I started, is 16.4 kilometers, but it's not really a displacement yet until I get an angle. So I use tan, so I know my angle in here. If I've measured it from our horizontal or east, that'll just mean that my first letter is going to be east right here. It's a little unconventional, but it's not the end of the world. And so tan to the -1, or inverse tan of 15 over 6, is about 67 degrees. So 16.4 kilometers east, 67 degrees north. All right, so that would be this angle right here. And again, that's okay. I prefer north 23 degrees east. And so that's just a different way of looking at it. That's looking at it from north, going in the easterly direction. And that's just more of a conventional thing. It shows that I've taught a lot of geography and not very much pure math. Again, so that is our final total displacement. We have added them up once we've broken them into their components. And then once we've got the totals, we've sketched it. We use Pythagorean theorem and inverse tan to find our angle, and we can put those together. And with that, you are off to your homework. You can use a template like this for solving things using component methods. Thanks for coming out. Know your history, know your physics.